All right, let's get started. Hi, everyone. So today we'll have Pablo Mercader Perez, who is a PhD student at MIT and a second-year PhD student. He's done some amazing work over the last year. And in fact, last week he had his first PhD paper accepted. And that's what we'll talk about today. So due to that, here we will represent it in July and Brazil in April. He's been doing some work disentangling signal and measurement artifacts. We're trying to build causal foundation models that he'll talk about. And he's worked with a group of others at MIT, and he's also supervised by Bill Freeman and George Ricker. So welcome, Pablo.
Hi, everyone. So as Anne said, feels very special to present this here today because this is a project that I started working on here at AstroAI last summer as part of the AstroAI summer program. So, and we recently had a paper accepted to the Foundation Models for Science workshop at ICLR. So it feels very nice to be able to share it with this audience. So this is gonna be the outline for the talk. So let me start by giving a little bit of motivation. So first, let me bring everyone to the same page about what we mean when we are talking about representation learning, right? So our representation of your data is just like some function of your data, and that typically you want it to throw away the information that's not relevant for you, for your task, while it retains while it preserves the information you care about for your task, right? But then, so then how can you actually learn this encoder, this function that will do this? In supervised learning, you might use labels for this. In self-supervised learning, you need some other way to get your learning signal. So this is where we come with the concept of pretext tasks. So the most common one is maybe reconstruction, where you might want to compress your image to a low-dimensional representation and then be able to reconstruct your original image. But this is not necessarily what you care about in the end. You might want to take these representations and use them for something else, for parameter inference or some other task. So this pretext task is just a way to get an objective function to be able to train your neural network. So presentation learning is tricky in astrophysics when we work with astronomical data. And this is one of the lessons from the first data released from Euclid when so people took this data release and they tried to train a foundation model with the AstroPT architecture on this data. And then one thing you can do is you can look at the representation space of this model and do a UMAP projection, and you might want to try to find interesting, physically interesting anomalies in this space. But then if you look for outliers in this space, what you end up seeing is that they're just dominated by these weird instrumental systematics or these instrumental effects. So these instrumental distortions are kind of shaping the geometry of this space. And just to give another example, here are two images of the same galaxy viewed by two ground-based telescopes, Legacy and HSC, and you can see in one of them you have this weird stripe that if you didn't have the image from the other galaxy, you would have no way of knowing if there's something under that stripe. And even more if you are trying to predict some galaxy properties from this image, you are going to be confounded by these weird instrumental distortions, right? So why does this happen? Well, we think that this is because in astrophysics, there's always some process that you're interested in happening somewhere in the universe. And this is going to generate light or gravitational waves or whatever interesting physics you're interested in observing. But then in practice, you cannot observe this directly, right? This is going to have to go through an instrument. And then your observation, your data is the result of the response of this instrument to the physics, right? So your observation is going to be a function of the actual physics, but also some variables related to the instrument. So which we kind of separate, in this work we separate into like science or physics variables and these other like confounding factors that come from the instrument. And when we talk about disentangled representations, what we mean is, can we learn a representation that separates these two sets of factors, right? And being able to do this is useful if you want to combine data from multiple instruments. If you want to be able to like do parameter inference unconfounded by these instrumental effects, and also if you want to like generate counterfactual views, such as like what would this data look like if it was captured with a different telescope, right? So in this project, we proposed something that we called a counterfactual generative objective, which I'll explain what that means. And with this, we achieve some disentanglement in our representations, and we show it in a setup with two ground-based Galaxy Imaging Surveys, Legacy and HSC. Before that, let me mention a little bit of previous work in this direction. So, as some of the people here probably know, there's been a lot of like work in foundation models in astronomy in like the recent years. Here's just like a list of some of the most relevant ones to my knowledge. I'm probably missing some, and you can see this is all like in the last few years. So it's kind of like a rapidly growing field. And I just want to highlight one of them, ION. So ION is arguably like the state-of-the-art foundation model in astronomy at the moment. It's like a 1 billion parameter model, and it's multimodal, which basically means like it can take like different data modalities like images, spectra, even like directly some like parameters, and it will like tokenize everything. And then it's like it's in practice, it's just like a masked out encoder. Well, it takes all these tokens from the different modality and it will encode them into some embeddings, and it also has some decoder. But like the interesting thing is that you can take these embeddings and you can use them for whatever downstream task you care about. Like you can use it for like doing regression on some like physical properties you're interested in. You can even make segmentation maps. You can try to retrieve interesting samples similar to the one that you're using as a query. But we think like one limitation that is common to this and all the other foundation models is that instrumental effects are either like directly ignored, or in ION, for example, they will treat, if they have images from two different telescopes, they'll just treat them as different modalities. So they treat each instrument as modality, so they don't like directly address these instrumental effects, and we think that this has impact on your downstream tasks and as a confounding factor. So some work in trying to address this was done by my collaborators at MIT and also here at CFA, I guess in this paper about causal foundation models. And this paper introduces an idea that is also very like foundational for my project as well, which is this idea of data triplets. So basically what they said is, well, in astronomy, very often we have two surveys that have a large overlap on the sky, right? So we have multiple observations of the same targets, right? So what they do is they say, okay, I have this star observed with a certain instrument, and then I have observations of the same star from other instruments. And I know that the underlying physics is the same because it's the same star, right? So I'm gonna try to learn a physics latent space, and then I'm gonna impose that the representations should look similar in this space. Particularly what they do is contrastive learning. So this is a loss that imposes that the two representations are aligned. And then in the instrument space, they do sort of the same, where they say, okay, I have these other observations from the same instrument on other targets, but I know the underlying instrument is the same. So I'm gonna learn an instrument latent space where the representations should be aligned. So again, they do this with contrastive learning, and there's a reconstruction objective. And then the thesis behind this work was that if we train in this way, we should be able to use this physics latent space for our downstream task and perform better because it's not like contaminated by like the instrument information, right? And they showed in this paper that indeed in some like stellar parameter regression task, they were able to get the same performance as with a like traditional like monolithic foundation model with only as much, only like 10% as much training examples. But like another thing so one issue they bring up in the paper is that when they looked at this like instrument latent space, there's some information about the stellar properties there as well. And one of the main reasons why we suspect this might happen is that this, at the end of the day, this instrument latent space is seeing like through this instrument encoder, it's seeing the original image. So it's seeing, it can capture the information about the signal in the physics information. So we believe that could be a source of leakage. But kind of like the state of mind we were in when we started this project is, can we come up with a method to improve this separation and get like even better performance, right? So this brings me to like the, sorry.
So just on the previous slide, so with the creating the physics latent space, so you said that you're assuming that the physics is all the same and it's only the instrument changing, but I guess how does your model work with like time variability of time, especially in things like stars, which can vary over
this is like a good question. So for example, if you have like some time series data, like my guess is this would only really work on like the periodic components of your signal if there's something that where like a phase shift is gonna make it change. Because, well, it depends if you have simultaneous observations or not. If your observations are not simultaneous, you can only hope to like capture the things that are like periodic signals, like you care about the period of pulsation of some star or things like that. But things that are aperiodic, you don't have them.
But I guess a follow-up question is how much noise would that? I guess TESS and suppose you're doing TESS and Kepler.
Yeah.
So those sort of observations aren't likely to be simultaneous.
Yeah.
So that's that. So is part of any variability or changes in the behavior of a star between those two observations likely to be interpreted as an instrument? Or is that unlikely?
I would assume maybe it could be interpreted if it doesn't happen on any other star. Like, unless you are like overfitting, but like if it's a one thing that only happens in that particular example, probably your model. But yeah, these are very good questions, and it's part of the reason why for now we moved to galaxy images.
Okay.
No, but these phase shifts should be independent of the instrument, right? So you're not going to see that same phase shift in other stars that are observed in the instrument space, and so you shouldn't expect that to be encoded. It's just two views of that object taken at different times. And so hopefully it'll, at worst case, will be interpreted as noise, not instrument.
So this brings me to like the method we are proposing in this project, which I guess without loss of generality, let me go to galaxy images now. It's time series data. Although, yeah, maybe there's some specific aspects to each type of data, but the idea is, again, we have galaxy, we have triplets of data. So we have a certain galaxy observed with one telescope, and then we have this that we are gonna call the galaxy pair. That we're gonna call the galaxy pair, which is the same galaxy observed in another telescope. And then we have something that we're gonna call the instrument pair, which is the same telescope as our anchor, but observing different objects. Right? And again, we're gonna have like a physics encoder that learns a physics space from this galaxy pair, and then an instrument encoder that learns some like instrument latents from this instrument pair. But now, like one big difference with the contrastive case is that none of these encoders see the anchor image. Whereas like before, both of them were seeing it. Now none of them see it, right? So this the only thing that this has in common with the anchor is the physics, right? And like the only thing that this has in common, the anchor, is the instrument systematics in principle. So okay, but then again, we need to have some like pretext tasks to like guide the learning of this encoder, because like this is very nice, but you need to encourage this encoder to actually learn this. Right? So the way we did it is we have a generative decoder. So particularly we're using flow matching. So flow matching is basically a method that's gonna and I'll go into more detail later about our implementation, but it's a method that's going to learn to transform a base distribution, in this case of like Gaussian noise, into a target distribution, which in this case is our galaxy images. And in this case, we're learning a conditional distribution conditioned on this instrument and physics latents. So basically, this decoder is going to go from this set of latents to a galaxy image. And so basically, we're learning this, which is like given some galaxy J on an instrument K, you're learning the conditional distribution on your like galaxy pair and your instrument pair. And in this notation, I'm already hinting that in principle you could use multiple pairs at the same time. Like you could take like many examples from the same instrument observing many different objects and combine all of them to do your conditioning. And same if you had like many instruments, in principle, you could use like n-1 instruments as galaxy pairs. So compared to the contrastive learning case, now we have this new ability to make counterfactual views, because even if this like anchor didn't exist, like even if I had never observed this galaxy 99 with HSC, I could still make this image, right? So I can do like hypothetical reconstructions of what would a certain object look like in with that telescope, and also you can leverage like more than one example of like multi-instrument data, and I will get into this a bit more detail later. To have a conditioning with like a variable length conditioning. So now going to like the implementation. Sorry.
So if you go back to so here your decoder is going to be this flow matching based.
Yeah.
Are the encoders the same that you had in the contrastive learning approach, or are they also probabilistic, or what? How are you?
They're slightly different. I have a slide about that, like in 2 slides. but yeah, no, they are not probabilistic. Yeah. I'll get to that in 2 slides actually. So so I'm gonna talk about the implementation now. So I just have 1 slide before that, which is about the data we used. So we used a cross-match data set from the multimodal universe of about 100,000 galaxy images from 2 ground-based telescopes, the DESI Legacy Imaging Survey, which we'll just call Legacy, and HSC. And then we did the same pre-processing as they did in the ION paper. The only difference is they cropped the images to 96 by 96. At first we did this, then we realized we didn't have 288 H100s like they do. So we cropped to 44 by 44. But I think most of like the interesting physics happens like in the center of the image, in your central object anyway. So,
by how much did your computing need reduce by making this change on the image size?
Yeah, well, I mean, this is going to be 1/4 as many pixels, right? And I don't think it scales exactly linearly. I think maybe this made the training like 8 times faster or something. And this already took the order of 1 day to train the models. But yeah, in principle, we could scale back to 96, right? And then we made this data triplets that I was talking about. And I mean, in this case, we only get 1 galaxy pair because we only have two telescopes, right? But we're very interested to try to scale these to settings with more than 2 instruments. I think that's when the true power of this method will come out. And then for the instrument pairs, in principle, we can get like almost an unlimited amount, right? Like we could get like 100,000 minus one instrument pairs. But we decided to restrict ourselves to looking for instrument pairs that we call like spatial neighbors. So things that are within like an angular separation of 3 arc minutes on the sky with respect to our anchor, because we noticed that then your correlation in noise properties is much stronger because you're going to have like similar observing conditions, right? So this provides a much stronger training signal. And then, so about the encoders, for each one of them, we used a ResNet 18, and we just changed like a couple of things, but very minor. So this is like the typical ResNet 18 architecture. So basically, we changed the input size to 48 by 48. Sorry.
I'll ask later. That's fine.
Okay. Feel free to say. Yeah, Mike.
Are you worried here that with each pooling, it's going to end up with just one pixel with very long set of problems?
Yeah, so we kind of yeah. So let me explain the slide because I might answer your question. So the thing with ResNet is like with the vanilla architecture, at the very end you have some like average pooling and like a fully connected layer to get like your logits for classification, right? For like ImageNet or whatever. So we got rid of this at the end and we replaced it with a 1-by-1 convolution. And then you can choose the number of channels, and this is going to be like your latent size, so to speak. So we use 16. And then if you kind of do the math of like, okay, this is 48 by 48. Here I get a downsampling of 3. Then here I get a downsampling of 2 because it's like a strided convolution. Same here. You're going to end up with like a 2-by-2 grid of features. And we thought like, wait, maybe this is actually like a feature, not a bug, because we get like a tiny bit of spatial information there. So we decided to kind of keep this way instead of doing the pooling. And then what we did is, well, we just turned this into like a tensor of like your batch dimension 4 and 16. And we treat this as like a sequence of 4 tokens of size 16. And then because we have one galaxy pair and n instrument pairs, you can treat this whole thing as a sequence, like you can concatenate everything and get a sequence of like 4 times n plus 1 tokens. And this is what we use for our conditioning. So we'll do like cross-attention conditioning on this, which I'll get to now. But does that sort of answer your question?
Yeah.
Okay.
Sorry, I have a question. So if you already mentioned, but did you use the 3-channel JPEGs of DESI or the 4-channel Fitzwise?
Yeah. So that's good. So HSC has 5 channels. DESI has 4. So we just decided to use 4 and 4.
Okay.
And we scattered the extra channel on HSC, but that's something we could think about in the future.
And did you use the pre-trained weights of the ResNet or you trained from scratch?
No, yeah, we trained from scratch. It would be tricky to use the pre-trained weights because, yeah, I guess another change is that your typical ResNet has 3 channels and we were changing to 4, right? So then we thought a little bit about like, okay, can we like have 3 channels that are pre-trained and 1 channel initialized from scratch? In the end, we went with untrained, like initialized from scratch. And I'll show some interesting results about what happens when you have an untrained ResNet too. Okay, so then for the decoder, which is maybe like the most interesting part here, we used a unit. So we used like an implementation from this package called diffusers, and we made like a few changes. So basically, like what your unit does is like it's gonna take this like XT, which is like a partially noised image. So this is in flow matching. This is just like some linear interpolation between a realization of your noise and your target image. And t is just like between 0 and 1, like how noisy it is. And then your ResNet tries to predict the velocity field, which basically this is like in image space, what's the like linear probability path between this distribution of noise and this distribution of images. So it's kind of like how do you have to transform this noisy image to go to your target image, right? And so ResNet kind of downsamples your input in like several stages, and then it has some like processing in the bottleneck, which is like the mid-coder, and then it upsamples again, and it has some like forward like skip connections. So it's kind of extracting some features at each stage. And then we condition this in two ways, which is maybe like the unconventional thing. So first, we do like time conditioning. So this is this like T number that tells the unit like how noised this image is. And for this, we do something called like additive conditioning on the ResNet layers. And this is pretty standard, I would say. Now the slightly more unique thing is we also do cross attention conditioning. And so the idea is we take this. So this is a tensor that's just going to be like all these conditioning tokens that I was talking about, like our latent space. So we have like our galaxy latents or our like instrument latents. And this can have a variable length as well. And then we're going to have an attention block between the features of each of these ResNets and our conditioning embeddings. So the unit features act as the queries, and the conditioning embeddings act as like the keys and values for the attention calculation. So basically, it's like extracting information from these latents based on this noise image. And then what's your loss function? Well, it's basically, I mean, this looks like a lot, but it's very simple. So you basically like sample some time t, and then you sample some galaxy j, some instrument k, and then you sample an image for that, right? And then you also sample a noise realization, right? And then this term here is just the ground truth velocity field. So the ground truth kind of like update that you would need, like the direction in which you need to move in image space to get to the target image. And then this is what your network estimates. That of course it depends on like your partially noised image on this like t value and all your conditioning latents. So this is how you calculate the loss function, and you update the gradients and everything during training. So now let me go to the fun part, which is the results. And if I kind of lost you, I guess this is a good time to reconnect, because like you don't need any of the previous to kind of I guess to kind of be able to contribute to this discussion, I guess. Like I'm very interested to know what people think. So I'm gonna show you two reconstructions from the model, and like one of them is going from a legacy image to an HSC image, and HSC is slightly like higher resolution, so this is perhaps the more interesting example, but I'm also gonna show that you can go the other way from HSC to legacy. So in both cases, these are our target images. They're 48 by 48 cutout of an image. And then this is the same object, the same galaxy observed on the other instrument. And this is one of the inputs to the model. And then we have some examples of the target instrument observing other things. So all of these are the inputs. And as you can see, I've put like 4 images here, because the idea is that we can condition the model on multiple images, right? And in the final training run that we show, we used 5, but you can ramp up this number as much as you want in principle. And then here's like, well, you run the model once, you get this reconstruction, which kind of looks like the target. It has like slightly weird feature here, but then you can like run the model again and you get like a different one. And then you can also do it many times, and this is kind of like your mean. Because the idea is that this is not like a deterministic thing. You are like taking samples from the posterior of your conditional distribution of galaxy images given the latence, given the latence you have extracted from all these inputs. This is like the distribution of possible images that you could get. Right. So this, and this is very interesting because you could imagine having something that is sort of at the limit of detectability with legacy, and then you want to know like what are the targets that are the most promising that they are going to show something interesting when you observe them with HSC. So we think this can be a very useful tool for like follow-up observation, like proposals or prioritization, because you have a data-driven argument as to which targets are the most promising. Right?
So sorry, just to clarify here. So you, after training, now you're passing. Your target is the central image, but the model is at inference time. The model is only seeing the same galaxy taken with a different instrument, and a bunch of other targets observed with the target instrument. And you want to say you're asking the model, how would the galaxy look like in this other instrument? I'm showing you this observation with this instrument, but I want you to show me the galaxy in the other instrument. Okay.
So the model is only seeing this and all of this. And for example, there's like some feature here, right, that you cannot really see in legacy, or it's very blurry. And then the model kind of accurately realizes that there's something there. It also kind of hallucinates here in this one sample. But when you look at the minutes, sort of there, right, and the other one is kind of... So it's, and I mean, kind of the same like down here, right? Like I wouldn't have been able to tell there's something here, but kind of the model makes like an informed probabilistic prediction, right? In some sense. So we're very interested to explore this for like strong lenses, for example. We have some like preliminary work on that. But let's also like look at the latent space, right, to see what's going on. So first, let's look at the physics latent space. And so what I'm showing here is like galaxy images from HSC and legacy, and the orange dots are HSC images, the blue dots are legacy images. And you can already kind of see that the two distributions are overlapping, they're aligned. So this kind of tells you that we've learned a representation that is somewhat invariant to which instrument we use to take the data. Right? And more like specifically like these markers of different colors, they show for a given pair, we take the HSC image and the legacy image and we look where they land. And most of them are very close together. Of course, this separation is not perfect, but like for most of them, the pairs look very close together, which again, it kind of tells you that your representation is for the most part invariant to the instrument you used.
So do legacy and HSC have the exact same filters? So I know legacy has GRZ, but I thought HSC had slightly different image filters.
Yeah, I think HSC also has GRZ, and then it has an extra one that we didn't use. In this case, we discarded that one, and then even the same filters, like the filters that share the same name, I think they don't have exactly the same central wavelength, I think. So there's like small differences. Like I believe this would like break down if you have like very different wavelengths where like the physics you observe in one wavelength and the other is very different, right? But I think for those 4 filters, they sort of cover more or less the same range of wavelengths. So that's why this seems to work. Yeah.
But in your HSC, do you use, for example, the I-band filter, even though in legacy you don't have the I-band?
So the one like the sorry, I don't remember exactly like the name of the band, but like the one band that is different, we throw away on HSC.
Okay, so you only use the band
channels. Yeah, we're keeping like for channels. Yeah.
It's kind of along those same lines. Maybe HSC and legacy images look quite similar. So that's why they're overlapping. Have you thought about doing, say, legacy versus DESI spectra, and then seeing if you get a similar result?
We haven't tried yet, but yeah, that's kind of one of the next things we would want to do is like extend this to other data sets, and maybe that requires some extra considerations if we go to like a multimodal setting. The other thing that we've been thinking is trying to compare a ground-based telescope with a space-based telescope. I think would be very interesting too. And yeah, definitely like spectra are also part of the conversation. I think, all this is like in our heads for like future work. And then if we look at the instrument space, well, now for the most part, it's pretty separated, where you have like some islands that have like all the legacy images and like a big island that has all the HSC images, and all the pairs are split as you would hope, as you would expect. There's still like some mysteries here as like why, like, so we get like a few legacy examples that are like similar to HSC, and so on. So we're still working on that, but in principle, this also shows that this representation is kind of capturing your instrument properties, sort of independent of whatever object, of the properties of the object you're observing, right? Like all of these things here that are very tightly clustered, we know they are all going to have different galaxy properties. Like you can see how like spread they are in the physical space, but then in the instrument space, they are all clustered together. Right? Yeah.
Do you have any indication as to why you have that blue cluster there? Like, is there anything particular about those galaxies that you could think could be confusing the model?
Yeah, I'm not super sure. I tried to look into it a little bit, and it just looked like very clean legacy images, like the least noisy legacy images, perhaps. Or yeah, I kind of wanted to see if they all come from like a nearby region in the sky. So I suspect they all probably have similar observing conditions. But yeah, we're still sort of working on that. Okay, and then this is interesting, but we kind of wanted a more like quantitative evaluation of what's like the information content and the disentanglement in our latent space, right? So in order to do this, we decided to evaluate on a downstream task. So what this means basically is like you can take the latents extracted by your model, and then you train another small model like an MLP on these latents to try to predict something. So imagine you take this image, like you encode it through both encoders to get like your physics latents and your instrument latents, and then you take this and you try to predict like what some properties about the galaxy shape, or like star formation rate of the galaxy, some properties about the instrument, like the PSF. And then we compared against ION on this task, and we also compared against like a randomly initialized ResNet 18, which is like the same architecture as our encoders, because as I will show soon, like we realized that like when you initialize ResNet 18 with the typical initialization, which is like timing initialization, it turns out to be a pretty good feature extractor already, even before training. So I'm gonna show the results first on like some physics-related properties. And we are combining like features from an HSC image and features from a legacy image. And this is kind of the result we got. So the blue and red are like our method with the physics latents and the instrument latents, and we're comparing with ION and this untrained ResNet baseline. And the properties are like some like the ellipticity of the galaxy, photometric redshift, total like star mass, effective radius, star formation rate, etc. So the interesting thing here is that first, like if we look at our physics latent space, we perform similarly to ION in most tasks, or like we get like a comparable performance, and this is already quite impressive given that our model is like a lot smaller and was trained for a lot shorter. And yeah.
I think it's interesting that, I mean, maybe it means nothing, but
Yeah.
you seem to perform better than Ion at Ion, whatever you pronounce that. That's tasks that are more sort of morphology related than physical quantities, like, I don't know, the star formation rate.
Yeah.
Maybe I would have hoped that because you've separated the physics from the instrument, you would be better than Ion at the physics. But you're also saying it's a much smaller model, so maybe if you scale it up, you'll see. But I'm surprised of the fit between morphology and physics here.
Yeah, and also like if you think about it, our latents are like 4 times 16, so like 64. In Ion, they have embedding, like they embed into like a sequence of, I don't know if it was like 1,000 tokens of dimension 700. So it's not even compressing. It's larger than the original image. So, which it's kind of surprising. But anyway,
Which Aeon did you use? Is it the 3 Ion base? Base. Okay.
Yeah.
And do you know how big your diffusion model was in parameter count?
Yeah, it's 200 million for the unit, which is like the bigger part. And then the encoders are like 10 million. So yeah, maybe actually it's not that different in number of.
Oh, comparable, I would say.
Yeah, like how much? So 1 billion is the large, right? Like,
as far as I know, no one can get 1 billion unless you're in polymathic. So you're probably using the 300 million parameter one.
Yeah. I think I'm using the base, which is probably the 300. Okay, yeah. So maybe it's actually not that different in number of parameters. It is very different in latent dimension. So I think perhaps the more interesting part is if you look at the instrument latents, right? They perform worse at this task, and you might say, well, they still get like 0.5 R squared, which is not that bad. So it still has information, right? But like when you look at the untrained ResNet, so this is literally the state of our encoder at the beginning of training, and it kind of does similar to that. So it's like, I think this is the true like baseline, right? Not the zero, because it's like even without any training, you could run the image through this ResNet 18 and use those features and get this like R squared value.
What do you mean untrained? Is this untrained for this task, or is it pre-trained on a general image?
Not pre-trained. No. You take a ResNet and you do random initialization.
Okay.
With timing initialization. And it's because of like the inductive biases that so that initialization. So it's kind of, you're not like really randomly initializing it uniformly with like a naive way. It's like a very well thought random function that like preserves variance, and that compared with like combined with like the inductive biases of your ResNet, such as like locality in the CNN, you have the skip connection, so the random weights don't really destroy all the information and so on. It's like a pretty stable feature extractor, which is why ResNets are good at the beginning of training. But that's like a whole like rabbit hole that we went down for like 1 or 2 days. But I think the more interesting thing is what happens when you look at like instrument properties. So we tried to predict properties from the legacy telescope, right? Such as like what's the full width half maximum of the PSF based on the image, right? And compared to, well, we see that like Ion, like if you train in a naive way, that's kind of similar to this baseline untrained ResNet that we came up with, maybe a little better. But then compared to this, we have some instrument latents that characterize the instrument better. So we have like a better data-driven instrument model. And at the same time, our physics latent space is doing worse in this task, even worse than it would do at the beginning of training. So we think that the like information bottleneck combined with this training objective has forced the model to like erase this information and sort of like learn to be invariant to these instrument properties, right? So and it's kind of the same with HSC. Like it's pretty impressive that like we have a model where like you can give it one image and it can predict you like what was the PSF of the telescope that was used to take this image, right? And at the same time, we have a physics space that kind of disregards this. So so we think that compared to like the traditional approach, right, like which would be represented by ion, I guess. In that approach, you retain this instrument information in your latents, and that's gonna like confound you when you're.
Pablo, what are you? So you're predicting with the latents the properties, and you're using like a linear prediction.
We're using an MLP. I think it's like a 3-layer MLP. It's the same thing they did in ion. I think they did linear probing and then an MLP. So yeah, so we use the same thing to make the comparison fair. And then one more thing, and this is the last thing I'll show, is something we realized we could do that we're calling like instrument invariant neighbor search, which is just fancy name, but oh sorry.
So on the topics of like the measuring the PSF size and things like that. So I guess so your model you're projecting from kind of one instrument to another, but if you're learning if your model's learning details about the point spread function, are you able to sort of deconvolve that from the images almost to get like a true sky image and or like a super resolved image for either telescope rather than converting from one to the other, but converting sort of to the true sky?
Yeah. So not really, but I mean not in like image space, but in some sense like the hope is that these like physics latents would be like the equivalent of that. Like if you had that like true sky image and you compressed it, you would end up with something similar to these physics latents. It's kind of the idea. We're kind of trying to generate what that looks like in image space is kind of like out of distribution. Like we can't really do that. Okay, so these like instrument invariant neighbor search. So basically, one thing you can do is you can try to look for like nearest neighbors in your physics space or in your instrument space. Right? Like say you have some galaxy or some object you're interested in, and you want to find like similar examples with similar properties. Right? So you could take either your HSC image or your legacy image as the query, and I'm going to show what you get for both. And then these are like the top neighbors, nearest neighbors in the physics space. So first of all, like interestingly, the top one neighbor is the other side of the pair. But then like after that, the following ones are like objects that have like similar properties, but they come from a mixture of the two surveys, right? Like when you query HSC, you get like HSC examples and also some legacy example and vice versa. And like more interestingly, like these 4 examples that I'm showing here, like they are the same in a different order, right? So you could have found these 4 examples independently of whether you use the HSC image or the legacy image as your query, right? So this, so we think this is very powerful in like trying to say you have like some object you're interested in and you're trying to look for things with similar properties in a different survey, right? So you can try to look for similarity search across surveys. And then the other side of it is if you look at the instrument space, you're gonna find things that have like different properties and different shapes, but a similar noise properties, like similar noise level, you can see here. Yeah, and then like here. Yeah, so to conclude, I think with our method we can sort of like separate the physics and instrument without having a like hand engineered loss. So typically work in this direction tries to come up with a loss function. We're just using like the vanilla, like conditional flow matching laws, but we are playing with like what's our target, what's our input. So in this way, we don't really have to like engineer a new loss function. And then with this method, we have this ability to do this counterfactual generation that, as I was saying, we believe it has a lot of potential applications to be explored. And then we can do this neighbor retrieval across surveys, which we also think can be very powerful. And in terms of next steps that we're thinking about, we are working on making a like side-to-side comparison with contrastive learning in like your performance in downstream tasks and your disentanglement of latent space and so on. We're aiming to have this for the camera-ready version of the paper, and then we want to think about applying this to other data sets. So we've been thinking about like light curves. I had a meeting where we were talking about using this on like radial velocity data for exoplanet detection as well. And I'm like personally very excited to try this in a setting with more than 2 instruments as well. And then one thing we've been thinking about is, well, maybe this in your physics space, you only capture like the information that is like robust across surveys or like shared across surveys. So maybe you might have like a separate like residual encoder, for example, for that 5th band of HSC or something like that. So if you have like some extra information from one of the instruments, you can store it in some sort of like residual latent space. Which we've been thinking about this. And just to finish, we are hoping to put this paper on the archive soon, probably once we have the camera-ready version. Let me finish by bringing up some acknowledgements, and I'll take more questions. Yeah.
One or two quick questions.
I have one question. You separated now the instrument model and the physics model. Is there something like a third layer in between? Let's call it the observational model, because when you observe each one of the surveys, you have weather conditions that your data, which are always different. You never have the same conditions.
Yeah.
Exactly. But they would affect either model, the physics model or the instrument model, but you want to tease them out because.
Yeah, that's a good point. And maybe this like, maybe like this, where is it? These like 2 sets of underlying factors view that I pictured here is a bit like idealistic, and you would have like a third set of factors that's like your noise that you sort of treat as
The rest in the kitchen.
Yeah, like a stochastic noise, right? Like, sort of the idea is within all of the things that traditionally you would treat as noise, there's some of them that you can predict from the instrument, right? And then you can kind of learn those separately. And especially those that are like not consistent, because it's like observing conditions and it's like a one-time thing. Like the best you can hope is that the model doesn't like overfit those and just reads them out noise and doesn't learn them right. I think. Yeah.
So when you say you're constructing your input data, so your pairs of images from the different surveys,
Yeah.
the like n images of galaxies that are part of this same image of your like anchor, are they also from the 100,000 like overall population, or are they taken separately from the surveys?
Yeah. So for the instrument pairs, when we say like, okay, other objects from the same survey, right? We actually took like extra images from the survey. So we had like a pool of like 300,000, whereas we only have cross-match for 100,000, right? But we can also use other non-cross-match data to have like a richer pool. So we actually did that. yeah, which it's also like a way to use more than just the cross match data, right?
All right, let's thank Pablo again for a great talk.